Good morning, students. Today we are going to learn B and B plus trees. So B and B plus trees are a DBMS concept, and they are used in databases to implement dynamic multi-level indexing. So to understand dynamic multi-level indexing, we first must understand what is multi-level indexing. So it's a bit of theory, but you have to understand the theory if you want to really understand this topic, have some context regarding this topic. So the theory is that there is a concept of blocks in DBMS. Blocks is a unit of data that can be transferred between the secondary memory and your primary memory, right? So if this is a block, then it can be transferred. The computer provides architecture to support this. You can transfer it from secondary memory to primary memory, and from primary memory back to secondary memory, right? Generally in today's architecture, the size of a block is 4096 bytes, right? Primary memory and secondary memory, I think that you must know. Primary memory is your RAM, and your secondary memory is your SSD, your hard disk, and so on and so forth. Basically the memory which keeps its data when the power is turned off. Primary memory is faster but does not keep its data when power is turned off. That is a fundamental difference. Okay, so now suppose that you have a file, right? Suppose that this height of primary memory is 4 GB. If you have 4 GB size of your primary memory, then you cannot fit files that are of bigger size than 4 GB inside of primary memory, right? So let's take an 8 GB file, and that 8 GB file is present in your secondary memory. So can you transfer that 8 GB from your secondary? Can you directly load the whole 8 GB into primary memory? No. So how can you work on that 8 GB? Right? There are applications. Obviously, you must have user computers, and your application sizes sometimes exceed your RAM sizes. The most obvious example of this are video games. The current generation of video games, AAA titles, are a lot bigger in sizes than the RAMs that are provided on computers. Normally 16 GB RAM is provided, and the size of the games are beyond 8 GB, 16 GB, sometimes even 50 GB. Right? So how can you how can you minimize the number of accesses? I mean, there is only a small amount of relevant data in the whole of 8 GB, right? If this is your 8 GB file, this is the file 1, this is your 8 GB file. So the whole of 8 GB is not going to be of use. Only at particular time this block may be used, this block may be used. So how can we access that data directly in your primary memory? Just load the data which is relevant, and just do not load the rest of them. That is the only way we can do it. That is the only approach that we can think of, right? That the constraints of the context enforce, basically, right? Now let's come back to this. If the storage of that 8 GB in the secondary memory was contiguous, right? Like this, if it was contiguous, then it would be comparatively easier if the primary memory wants to access this data that is present at yth block from the start of the file, from the start of the 8 GB file, and at the xth record inside of that block. Then it could have directly accessed it without any problems. But the secondary memory, right, it does not store data contiguously. Contiguously means one after the other, the first block, then the second block, third block. It actually stores it in the form of a linked list, right? This is one block, and after that block, it has a pointer to the second block. The second block has a pointer to the third block, and so on and so forth. Pointer, computer science concept, pointer is basically nothing but a data storage of the location of another memory location, any memory storage location, right? The only difference here that what I'm using pointers here is, normally when you use pointers, we use it in the context of primary memory, but here the pointer here is of secondary memory pointer, block pointer as we call it. So block pointer are storing the secondary memory address of the second block and then the third block, and like this in the linked list format, the whole 8 GB of that file is stored. Now suppose that if you want to access that yth location data, then you would have, if it's a linked list, then you would have to traverse to the yth block, and then you can take the exit record from it. But that would consume for that to happen, a lot of memory access and memory read and memory write must happen. The first block is loaded, then from it the pointer is for the second block is taken out, and from that the second block is then loaded, and third block is then loaded, fourth block is loaded, and then so on and so forth. So this is not a very good way of doing it, right? So how can we do it in a better fashion? That is the point. So let's understand how they basically have figured this out. There are a lot of very intelligent people obviously in this world that have worked on this and then figured out a very good way, and that is what is the concept of multi-level indexing. Let me explain. Suppose that this is the 8 GB block, right? 8 GB file, right? So it is broken down into a lot of blocks, right? And all these blocks are connected through pointers, right? But we are just representing it in a contiguous manner. They are not in actual fact in contiguous manner, right? So we can actually create another file. Let this be file 2, right? File 2, and this file has over here the block number, right? This is the yth block from the top, right? This is the block number, all the block numbers. Suppose there are, I'm not actually calculating, but suppose if there are 1000 blocks here, right? So if there are 1000 blocks here, so the first one would be 1, 2, 3, 4, and then 1000. And in the second part of every record inside of this file, it would point to the respective block like this. Okay. So once we have all of these records present, we can directly access the blocks. We don't need to traverse the whole linked list. The problem with this was that suppose that the file, the size of this file is greater than a single block, because this file is also going to be stored inside of your secondary memory, and if it cannot be stored inside of a single block, right, then it has to be stored in 2 blocks. One way could be that load this first file also, first block and second block, and then construct the file inside of memory and then do it, right? And that will involve a lot of work. But why not employ the same concept of providing a file to differentiate, to store the addresses of blocks again? So we created another file here which is going to store the addresses of, this is the file here, which is going to store the block numbers 1 and 2, and then those block numbers would have the corresponding addresses of the file which of the address file. This is an address file which is again broken into memory blocks, right? I hope that you are following. I'm explaining it in a very clear manner only. I mean, if you find that there could be some improvements, please mention in the comments down below. I will improve accordingly. Okay, so this is the basic concept of multi-level indexing. Now look at this concept. So you cannot start with 2 levels or define 4 levels or 5 levels and then work with that, because you don't have the guarantee that the files are going to be of 8 GB or of 4 GB or of 6 GB only. No, files can be of 2 GB, they can be of half a GB, right? So we want these multi-level indexing to be the computer basically deciding how many levels it needs and implementing it intelligently, right? We want the computer to do it. So if you want computer to even apply a small amount of brain on anything, you must have algorithms and you must have data structures with extremely clear rules. For that, this is exactly why the concept of B plus tree was invented, to basically handle this multi-level indexing automatically, right? So to handle that to apply that automaticity, you must now we are understanding, if you want to understand B plus tree, then you must understand the rules and the algorithm of the B plus tree, insertion algorithm of B plus tree, that automatically allows multi-level indexing to be spawned, right? B trees cannot be directly used in this context, but B plus tree can be used. But the concept of B plus tree is based upon B trees. So first I'm going to explain the B tree, then I'm going to explain the B plus tree. So let's come to here. So these rules are applicable to both B and B plus trees, and this is an example of B trees. Once you understand B trees, then you're going to be able to understand B plus tree also. So let's move ahead with it. So the first rule is that the ceiling of m by 2, first I would have to explain a node of a B tree, B plus tree also. A node of a B tree can contain multiple values, keys, right? Normally binary trees have only one value inside of each node, but in B trees it can have multiple values. So in B trees, the values that can be stored inside of a block are multiple. So for example, 1, 5, 7 can be stored inside of a block, but and the maximum number of elements that can be stored inside of a single node is a property of the whole of B and B plus tree, and that is, we are denoting that property by m, right? So let's assume that the property of this this node belongs to a B tree which has a property of with m is equals to 5. So right now it has only 3 nodes, right? But with 3 nodes it can have a total of 4 children, and those 4 children are representatively shown like this, right? So it has 3, so it can have m, whatever is the current number of keys that are present inside of a node in a B or B plus tree, then let that number of keys that are present inside of a node be represented by x, then it can at that moment have x plus 1 children. That is a rule. Now once we have understood a small amount what is the node, now let's get back to this rule. So m by 2 is the ceiling of which, for example here m was 5, so m by 2 would be 2.5, right? 2.5. Ceiling of m 2.5 is going to be the least smallest integer just greater than 2.5, right? And that is going to be 3. So at so this is what this m by 2 ceiling function means. So m by 2 ceiling function minimum number of children must be present in all nodes except root. So if a node is present that is not the root and it is any other node, be it the leaf node or an internal node, must have at least m by 2 ceiling. That is, if it is 5, then it must be 3 number of children must be present for that node, right? Right now this fulfills the property because it has it can have 4 children. It does not really imply that it can hold. I mean, it is not that it must hold, it can hold. Suppose the value of this can be null also, but by this x plus 1 number of children holding property, it must have the capacity to hold. That is what this rule implies. This is the first rule. Now let's move on to second rule. All leaf nodes must be at the same level. For example, this is a leaf node and this is a leaf node. The level of both of these nodes is same, right? Another tree that also has this property is called balanced tree, right? Balanced binary tree, you must have heard that concept. This is where the B comes from, of the B and B plus tree. This B implies balanced, right? Balanced. Now so this part we understood. These are the fundamental rules that we are just going to use to build this tree, right? So root node must have minimum of 2 children. So root node is given a relaxation to this m by 2 ceiling function property, and because if it is not given the relaxation, then the tree construction cannot start. So it can have minimum of 2 children, and because this x plus 1 property, I mean, if a node has a single element, suppose say 2, then it can have 2 children. So this property basically means that every root node must have at least 1 key. This is what this means. And the fourth rule is that nodes are added from the leaf level upwards. So from the leaf level you just add the node, and then if at particular level the node exceeds the maximum occupancy, that is, for example, here the maximum occupancy is 5. If it exceeds that, then we are going to adjust the nodes upwards. I'm going to show this by basically constructing this binary tree, this balanced tree, B tree. Okay. So now we are going to construct this tree. So let's just write down the whole thing. 3, 4, 1, 2, 5, 7, and let's add another element 6, right? So we have a 3. We have 3 as the first element. So we're going to add it to the root. So this is the root node. M here is equals to 3. That a maximum number of elements that a node can contain is 3. So first we add 3, and this agrees with all the properties, because the first property does not hold here because it is the root. Second property here, it is the leaf node. Yeah, this is the leaf node, and there are no disbalanced nodes because it is a single node present. So trivially it is balanced only. Okay. The root node can have 2 children. Yes, it has a single element, so it can have two children. Very good. So that property is also fulfilled. The nodes are added from the leaf level. That property is also fulfilled. So now 3 is added. Now we can add 4. 4 we can add after 3, right? So 4. Should we create another level, or can we directly add 4? There is no limitation. Look at the rules. There is no limitation of any sort being present that the new node cannot be presented into the same node till the maximum occupancy is filled. But obviously, because B trees also hold that the keys must be have a order to it, right? And that order is, I have written it here also, that this less than equal to order must be present inside of B trees. So because 4 is greater than 3, so it is going to be present after 3. Now this node can have 3 children, right? That is the maximum number of children that you can have either ways, right? So now, no, this M is here is not 3, this M here is 2, right? The M here is 2 because the number of elements that are present inside of a node here is 2 only, and M plus 1 here would be 3. That is the number of children. Sorry, it's my bad. Now we can add 1. 1 is less than 3. Yes. So we move to the left side here and add it here. Create another node and add it here, right? Then 2 is also less than 3 is greater than 1, so 2 we can add here. 5 is greater than 4, so we can add it here. 7 is greater than 5, so we can add it here. Now 6 we can is greater than 4, greater than 5, less than 7. So right now, as you can see that we will add first. We will balance it out later. We first add, right? This is the rule. So we add 6 here. Now this node has 3 elements, but the maximum occupancy is of 2 elements. So how can we handle this? Well, as I said, the nodes are added and then leaf upwards, right? In the leaf nodes, the new keys are added and then they are adjusted upwards. So because it has 3 of them, the 6 from here is going to go up into this node, right? And I know that this node is going to have more elements than should be present at that point, but we can do that, or we can also adjust. No, we can also adjust it here. Let me first explain that, but it will go up only. But let me explain it this way. Suppose that this becomes 3, 4. I'm not sending the 6 directly up. This becomes 6. This becomes 5. This becomes 7. Right? If I do it this way, then the rule that it must always be balanced is going to be violated. Hence, I must take this 6 and take it to the root node directly here. So let's add it to the root node, and we have 3, 4, 6, 1, 2, 5, 7. Right? We have it like this. Now we know that this has more elements than should be present, so we take 4 above. So we have 4, and then we have 3, then we have 6, then we have 1, then we have 1 and 2 here, and then we have 5 and 7 here. See how the whole all the properties that it should be balanced is also met. The property that it should be that each node must have m by 2 occupancy is also met, because 2 by this 2 by 2 would be 1 only, so every one element are present in each node. And root has minimum of 2 children. Yeah, it has minimum of 2 children, right? So, and the leaves are at the same level. So this is a B tree that is formed here, right? So now as you see, this less than property that is present in B trees, in B plus trees the same property can be modified a bit and can be said as less than equal to. And here duplicity of elements was not present. If 3 is present only once, even though it is an internal. This key is present in an internal node, right? The last level of your tree is your leaf nodes. All the other nodes inside of the tree are internal nodes. So even though 3 is present inside of a node that is 3 is present inside of a node that is an internal node, still its duplicate is not present in the leaf. That is where B trees differ from B plus trees, because every key that is present in an internal node must also have a duplicate in the leaf node. That is a difference in B plus trees. Let me explain, right? So if this is the basic B tree, then its equivalent B plus tree would have this 3 and 4 also present in the leaf level. That is a fundamental difference that is present, right? So now we as you can obviously see that when you had 1 and 2, then 3 must be added here also, and 4 must be added here also, right? This is what B plus tree is, because it checked for less than equal to. When it added 3, then it also checked. When it added 1 and 2, and then it checked in itself that okay, 3 is less than equal to, right? It added it in an internal node, and then went ahead and then checked for less than equal to, and added the 3 again in the leaf level. This is how B plus trees are created. Now just one important observation here that I must tell is that now at the leaf level all the keys are present. That is something which is extremely relevant to what we discussed earlier, that in the end all the data of the file has to be represented in an upper level, right? Upper level file in the end has all the block pointers to all the blocks of the file, of our file, right? So this is exactly which is filled. That requirement is filled because all the keys are present, right? If for example instead of a key you push in a data structure which has a key and a a block pointer, and this is the data structure which is present inside of leaf nodes only, right? In above internal nodes they can only have the keys but no block pointer, but in leaf nodes you can have keys with a block pointer. Let me draw it again so that you can understand it better, right? So 3, 4, these are only keys, they don't have a block pointer attached, right? B plus trees are a modified version of B trees. I'm just explaining, listen, right? Then we have 1, 2, 3, 4, 5, 6, right? So now in B plus trees there are basically two differences from your B trees. First is of the excluding, there are three differences. For the first difference is that your duplicity of keys must be present, and all keys in all internal keys must also reflect in your leaf level. That is one thing. The second one is that the internal nodes would only have the key values, but the leaf level nodes would also have can have this block pointers along with your keys. We use these block pointers to actually store the locations of the actual blocks in the secondary memory. This is your secondary memory. This is your 8 GB file, let's assume, and these block pointers of the leaf level. Now one more thing, the third difference would be that these leaf level nodes also have a pointer inside of them to the next leaf level node. This is only present in B+ trees, and this is can be actually useful because obviously they basically break the file. I mean, if you were to see it here, right, this is again broken into multiple files like this, and another level is added, but along with that this block is having a pointer to the second block. This is a fundamental difference in B+ tree that is also introduced. Can have multiple uses. Suppose that you have accessed this file and then the next one is required. Why go back and then go here? Just provide another pointer here. No, right? Because it's another level of abstraction. The first level is here, this is like another level. So there some use must have been found. So this is also introduced in B+ trees. But now I hope that you're able to understand how we are basically break. This is the actual file with pointer connecting with pointers, block pointers inside of that inside the blocks of our 8 GB file connecting one another, right? And then this is our file addressing file, which is divided into two blocks, and these two blocks are also connected by a pointer, right? And those two blocks location are stored inside of another file, which may or may not be able to be stored inside of a block. If if it cannot be stored inside of a block, then another level is going to be added, just as we are adding here in B+ trees. And that is how the B+ trees are used to have multi-level addressing, but because it is the level of that multi-level addressing is decided at runtime, hence it is called dynamic multi-level addressing. Dynamic meaning done at runtime. So this is why it is called, it is used. B+ tree is a data structure with its rules, that is with its rules facilitate the usage in dynamic multi-level addressing, and hence it is used there. That is the whole story of it. Dynamic multi-level addressing. Hope you understood something useful from this video. If you have some suggestions as to how I can improve, please do point them out in the comments. Like and subscribe. And I'm new to this, so I would highly appreciate any constructive criticism. And have a good day.